Hi, I'm Paige, and I'm going to be speaking to you today about plans for an absolute reactor anti-neutrino flux measurement with a neutrino detector called Prospect. The goal of my work is to use fundamental neutrino physics to monitor nuclear reactors and prevent potential diversion of fissionable material for weapons purposes. So we can start with some context. Inside the reactor core, fission produces unstable byproducts, and these fission products undergo beta decay and produce neutrinos, specifically electron-flavored antineutrinos. And about 6 of these reactor neutrinos are emitted isotropically per fission, and they're somewhat low energy. And here in this diagram on the bottom left, you can see an example of the flux and energy spectrum of those neutrinos and how they correspond to the mix of fission isotopes inside the reactor. So if we can make a precise measurement of the neutrino flux coming from the reactor core, we can essentially measure the physical inventory of the reactor in real time. And it's also important to note that because the reactor core is an isotropic source of neutrinos, the inverse square law applies, so the intensity of the signal will fall off with distance squared. Something we can pursue with Prospect is a precision measurement of the absolute reactor neutrino flux, and the motivation behind this measurement is very compelling. Essentially, there are different methods to predicting reactor neutrino flux. So you could compute the antineutrino spectrum from basic principles, but the lack of isotopic decay information leads to high uncertainty. And there's also a second method where previous measurements were taken from the betas from all fission products in a research reactor, and we convert the beta spectrum to antineutrinos using energy conservation. And we can use a combination of these two methods to predict the flux, but when we try to measure it, the observed reactor neutrino flux doesn't agree with the predictions. So you can see here in this plot on the right that if we divide the measured flux by the predicted flux, the ratio sits a bit below 1. So there's this clear deficit evident in the majority of the measurements, and we want to know why. So potentially the reactor neutrinos are oscillating to a sterile state, and we'd want to discover that. Or maybe the flux predictions we made are wrong and overestimated, and we just need to correct our models. So we can try to make this measurement to answer these questions using Prospect, which is a near-field segmented antineutrino detector that was first deployed about 8 meters from the core of the high-flux isotope reactor at Oak Ridge. And the segments are filled with 4 tons of lithium-doped liquid centimeter, and double PMT readout of each segment enables position reconstruction of events. And the segmentation suppresses cosmogenic backgrounds. So like many neutrino detectors, Prospect uses the inverse beta decay process to detect electron antineutrinos, which happens where the electron antineutrino comes in and interacts with a proton in the simulator to produce a positron and a delayed neutron. So we'll pay attention to the position of this positron later. After a 7-month run near Haifa, Prospect demonstrated high statistics and a world-leading precision in a uranium-235 spectrum measurement, which demonstrates that it's capable of making an absolute flux measurement. And Prospect is also being upgraded to a second phase, which will be capable of higher statistics and better background rejections to make even more precise measurements. So we can use this study to inform the Prospect 2 analysis. The relevance of this work to the NNSA mission is very direct. Plutonium is produced at reactor sites as a byproduct of nuclear energy production and can be separated from spent fuel by reprocessing. So because it can be used to manufacture nuclear weapons, we must, as a result, find some way to verify that no fissionable material like plutonium is being diverted from reactor sites for weapons purposes. So safeguards and international agreements are already in place, such as surveillance, IAEA in-person inspections, and fuel tagging, and more. but these are sometimes prone to errors or spoofing, and there are gaps in this monitoring regime with states opposed to the intrusiveness of inspections. So neutrinos from the reactor core provide a signal that's not easily spoofed or shielded and thus can be monitored remotely. And anti-neutrino detectors like Prospect offer a less intrusive monitoring option to deter weapons usable nuclear material from being diverted clandestinely from nuclear reactors for weapons purposes, as long as we can make this accurate and timely flux measurement. When it comes to carrying out the flux measurement using Prospect, we use the IBD event process to detect the antineutrinos, and then we can inform our measurement using our predictions for the reactor neutrino flux and express the flux in a model-independent way. So this process is dependent on different factors like reactor power, fission fractions, and isotopes, detector lifetime, etc. And because we have such high statistics and such strong background rejection, the uncertainties are mainly in the systematics. So as we set up a foundation for the absolute flux measurement, we have to characterize how well the systematics of our detector are known, because the entire measurement is pretty broad in scope. So for example, in the segmentation of the detector, you see there's this z-axis along the length of the segments. And in an absolute flux measurement, we need to reconstruct the z position of the IBD positrons and fiducialize. So if we plan to fiducialize to a certain centimeter length in z, we need to know if we're actually making this cut where we're saying we're making it, because that uncertainty will contribute to the uncertainty of the entire measurement. So we can use calibration sources to determine this. So we have some gamma and neutron sources, and what we do is attach them to a timing belt that is driven through the detector and periodically deployed at different predetermined locations along the length of the segment, as you can see here with the motor. And hundreds of these scans were taken with different sources at different deployed locations. And when we reconstructed the z positions of these sources, we found that those positions were slightly offset from the expected locations. So you can see on the left that this trend exists as we pull the source across the z length of the segment, that it has a very subtle positive slope, which corresponds to a sort of stretching of the fiducial volume. So now that we know this, we can use it to inform our fiducialization choices for future analyses. And from this preliminary z position reconstruction study, we can look at the mean offset in the z reconstructed positions on the left and know the range between our z cut length is plus minus 30 centimeters, and use that compared to the full fiducialization length to estimate a systematic uncertainty. And we noticed that we could even push our cut out to maybe even 40 centimeters and see if that changes the uncertainty, because nothing crazy is happening out there. And so basically, based on the stretching in z we see over all those calibration scans, we can estimate an uncertainty in the z measurement to be order of half a centimeter. And when we factor in the sigma of the spread, from the spread of the reconstructed positions, it turns out to correspond to around order 1% uncertainty. And if successful, this work can be significant in many ways. In terms of the fundamental physics, we could learn more about why the predicted reactor antineutrino flux doesn't match the measured flux, and explore theoretical solutions to explain that observed flux deficit. And then, as mentioned before, the capability to perform a precise and timely measurement of the neutrino flux and energy from the reactor translates to real-time verification of reactor status and fissile content. And Prospect-like detectors also provide high statistics for relatively low cost. So it's a realistic and viable option for monitoring. And in establishing international non-proliferation agreements, we can recognize it's necessary to balance intrusion and confidence. So safeguards must not interfere with ongoing operations and are fundamentally a form of cooperative monitoring. So non-intrusive detectors, which are capable of measuring absolute neutrino flux, build confidence within these limitations. And there's the added element of scientific engagement within the community as a development tool. MTV support can also positively impact this project. There's the opportunity to pursue a major hardware upgrade to the prospect detector for the second phase of its data taking through collaboration with Oak Ridge and Yale. And software development and simulation studies take place through Livermore National Lab. And additionally, there's other opportunities for piecewise R&D, including development and testing of PMTs and liquid simulator at Yale and Brookhaven. And future deployment potential at different national labs or research reactors supports personnel transitions and connections. And there's even the potential to perform studies to demonstrate how well a future prospect-like detector could monitor the power of a commercial reactor. And prospect collaborators include various national labs and universities across the US and Canada. So while this is a preliminary study, it tells us that we're on track for a 3% measure of the absolute flux with an order 1% systematic uncertainty in the fiducia z-cut. And we can keep in mind that if we were to increase the z-cut based on this study, it would actually allow for higher statistics with larger fiducia volume and decrease the fractional uncertainty in the z-cut. So we've taken the first step in constraining the systematic uncertainty in the fiducial cut, which we know is important because, like we said, the systematics are the main source of uncertainties in the measurement. And we can also remember that Prospect 1 wasn't specifically designed to pursue an absolute flux measurement, so this is just an added bonus. And in general, this analysis works towards the long-term goal of providing a non-intrusive method of monitoring reactor fissile inventory and intensity in real time to prevent diversion of weapons usable fissionable material, which is directly in line with the NNSA's mission of preventing the spread of nuclear weapons and reducing the threat of nuclear terrorism around the world.